Determine the tension in the string while the system is at rest. Okay, let's take a look. So this is the Prelim exam 2025 paper 1. Block A has a mass of 5 kgs and block C has a mass of 3 kgs. Block A is placed on a rough table with a coefficient of static friction of 0.2. Block A and block C are connected via a light inextensible rope over a frictionless pulley, and block B is placed on top of block A. It's shown in the diagram below. The system is only just at rest and on the point of sliding. Right. And then 2.2, determine the tension in the string while the system is at rest. So there's tension between A and C as they are connected by a light inextensible string. So A, I'm very hesitant when it comes to using A because there's B on top of A, of which I don't even know the mass of B. So it's better if I try find a way to use C in order to find the tension first. If that does not work, then I'm going to be forced to use A and B. But initially, it's better if we start with C because we have all the variables that we need with regards to C. So let's take a look. 2.2. So what can we do then? So first things first, we need a free body diagram, obviously, just to see what is happening, right? I don't even know if the free body diagram is going to come in handy, but I want to see what is happening. I want to be one with the question, right? Understand the situation, see what is going on. So first things first, there's weight, right? Because weight is always there, right? So we have weight. What else do we have? It's hanging on a string. So we have tension, which is upwards, right? So we have tension. So when it comes to C, these are the only two forces that we have. And these two forces are equals to each other. As the question says, the system is only just at rest and on the point of sliding. So we know that the tension is equals to the weight. Right, so there we go. We can use C in order to find the tension. We'll say that the tension is equals to the weight. We know that the weight is mass multiplied by the gravitational acceleration. So that is going to be 3 multiplied by 9.8. Right, and now I just need to substitute that in my calculator. And then says 29.4 newtons, right? Because it's tension, it's a force. So there we go, 2.2, pretty much straightforward. Let's take a look at 2.3. Draw a labeled free body diagram showing all the forces acting on block A. So first things first, weight, right? And then we're going to think after, right? So we have the weight. Now we can start thinking. So we have the weight. We have the tension as well because A and C are connected by a string, right? So we have tension going to the left, and then we have some coefficient of static friction. So that tells us as well that we have some frictional force, which will be in that direction. It will be to the right because the system is about to start sliding to the left. So the frictional force should be to the right. So that is tension, frictional force. Weight, what else do we have? Is resting on a surface, right? A is resting on a surface. So obviously we're going to have the normal force, right? But on top of A, we have B. Obviously B exerts a force on A downwards. So we have weight and the force as a consequence of B. As for which is greater than which, it does not really matter. You can make FB to be greater than weight. You're still going to get all the marks. Because at this point, when you're drawing the free body diagram, well, we know the weight, but we don't know the mass of B. So we cannot conclude and say whether FB is greater than weight or weight is greater than FB. All options the two options are going to be fine. So that is 2.3. Let's take a look at 2.4. Right. So 2.4. What is happening? Calculate the minimum weight of block B needed to prevent block A from sliding. Minimum weight of block B needed to prevent block A from sliding. So let's see. We have a free body diagram here. So where does block B feature on this free body diagram? We have the tension. We can equate the tension to the frictional force because we know that those two should be close to each other because the system is only just at rest. So let's see. we can say that F net is equals to MA, right? And then the tension minus the frictional force should be equals to 0 because the system is only just at rest. So what are we saying? We are saying that the frictional force is equals to the tension, right? And then here in the frictional force is where we are actually going to have the mass of B, which we are looking for. So we're going to have the coefficient multiplied by the normal force being equals to, well, maybe I should write that a little bit closer. The coefficient multiplied by the normal force being equals to the tension. We know the value of the tension is 29.4. So the normal force in this instance will be, right, let me calculate the normal force, will be the mass of A, which is 5, plus the mass of B, which is what we're interested in essentially, multiplied by 9.8. So we have multiplied by 9.8. So the normal force 5 multiplied by 9.8, that is 49 plus 9.8 mass of B. So there we go. We're going to have the coefficient, which is said to be 0.2. So we have 0.2 multiplied by 49 plus 9.8 mass of B. And this is equal to the tension, which is 29.4. So what I'm going to do, I'm going to divide both sides by 0.2. And then when I do that, 29.4 divided by 0.2, that is 147. So 9.8 as MB, the mass of B, is 147, minus 49, which is 98. So the mass of B is equals to 10 kilograms. So calculate the minimum weight of block B. Oh, the question says the minimum weight. So I'm not actually looking for the mass. I'm looking for the minimum weight. So needed to prevent block A from sliding. This is the grade 12 final examination. Like the grade 12 final examination. The examination that decides the future of most people. So let's take a look at what's happening. So Friday, the 31st of October is mathematics paper 1. And on the following Monday, the 3rd of November, is mathematics paper 2. Right, that very same week that you write mathematics paper 2, you write physical sciences paper 1 on Friday. And on the upcoming Monday, you write physical sciences paper 2. But let's be honest with each other. There's still a few topics that you're struggling with in math and science. If you go to my YouTube bio, you'll find 3 links: book one-on-one session, course, and email. So where you want to click on is book one-on-one session. You've taken a step in the right direction, and now it's time for you to book a session with me. One-on-one session is focused support tailored to your needs, and the group session is an interactive session for you and your friends. So you can invite your friend, a few friends, and then we can have the session together. So let's say you want to book a one-on-one session. So you're going to click on that. You'll decide on how long you want the session to be. Do you want the session to be an hour, 1 hour, 30 minutes, or 2 hours? Let's say you want the session to be 2 hours, right? So now it's time for you to select a date. Let's say you want to have the session on September the 4th. So you're going to click on that. And after you do that, you're going to see the available times. So if 5 p.m. work for you, you're going to click 5 p.m. And if 6 p.m. works for you, you're going to click 6 p.m. So let's say you want to book a session for 6 p.m. So you're going to click that. After you do that, there's a few information that I need. First things first, I need your name. So let's say, for instance, your name is John, right? The second thing I need is your email. So john@gmail.com, right? And then I need your number as well. Another important detail that I need is the topic that you need help with. So let's say, for instance, you need help with acid and bases, and to be specific, pH calculations. If you have any further question, you can WhatsApp me or give me a call on the number provided, or leave a question and I will give you a call, right? And after you do that, you just need to make a payment to the account provided based on the amount of hours that you want. Final exam is around the corner. You need to act right now. Can't wait to hear from you. Okay, so the minimum weight will therefore be 10 multiplied by 9.8, which is just 98. Yeah, 98 newtons. Yeah, I almost missed the point right there. I knew the physics, but I almost missed what the question was looking for. So, right, that is the weight. So, essentially, it implies that we can just set up an equation for the weight at this point as well and just use that. Yeah, but ultimately, we should get a weight of block B being 98 newtons. Here we go. Let me know which video you want me to do next in the comments. This doesn't usually happen, but this is quite a special question. Why am I saying so? Take a look at 3.4. Calculate the coefficient of kinetic friction between the 4 kg block and the surface. We don't usually calculate the coefficient of friction, but in this question, we have to do exactly that. But before we do 3.4, let's take a look at 3.1. Draw a labeled free body diagram showing all the forces acting on the 4 kg block. Let's go through our question statement and see what is going on. So we have a force of 51 newtons that is applied to the 7 kg block parallel to the horizontal surface, as we can clearly see, causing the blocks to accelerate at 1.23 meters per second squared in the direction shown. The 7 kg block experiences a 12 newton frictional force as it moves to the right. So we want a labeled free body diagram of all the forces acting on the 4 kg block. Here's the 4 kg block right here on the incline. So let's go ahead and draw a free body diagram for that 4 kg block. Well, let me draw it in 3.2 on the space provided. So first things first, we need the weight, right? So there we go. We have the weight. We can worry about everything else. Our object is resting on a surface. So there's a normal force that the surface is going to exert on the object perpendicular to the surface. So there we go. We have our normal force. What else do we have? There is tension force that is pulling the object upwards, right? Not upwards, but up the incline rather. So we have our tension force. And then ultimately, we have the frictional force going down. So let's take a look. This is the normal force, tension force, the weight, and the frictional force. We have 4 forces in our free body diagram, and we have 4 marks in our equation. So we are quite convinced that we have been able to identify all the forces acting on the object. 3.2. Calculate the magnitude of the tension in the string that joins the 2 blocks. We actually can't use the 4 kg block to calculate the tension. That is because at this point we don't have the frictional force or the coefficient, so we cannot use the 4 kg block. But can we use the 7 kg block? Let's go ahead and find out. We'll start with its free body diagram, right? Because as soon as you sketch a free body diagram, it's easy to identify the forces and substitute correctly. So the 7 kg block, first things first, we have the weight. Obviously, we have the applied force, 51 newtons. We have the normal force. What else do we have? We have the tension force, and the frictional force. So we can use F net is equals to ma. We have the mass, we have the acceleration, and then we have the forces acting on the object. So we will say force applied. This is the force pulling the object minus all the forces that are opposing the motion. So that will be the frictional force and the tension force. This is equals to ma. Force applied is 51 newtons. The frictional force is said to be 12 newtons. There it is. So 51 minus 12 minus tension is equals to the mass, 7 kgs, multiplied by the acceleration, 1.23. So 51 minus 12, that is 39. So we have 39 minus the tension being equals to 7 multiplied by 1.23. That will give us 8.61. So minus the tension will give us 8.61 minus 39. That is minus 30.39. So minus 30.39. If we divide both sides by the tension, not by the tension, but by -1, we'll get the tension being equals to minus, not minus, but plus 30.39 newtons. So there we go. We have the tension. Let's take a look at the equation that follows. 3.3, calculate the magnitude of the net force acting on the 4 kg block. Well, we know that F net is equals to ma. We do have the mass and we do have the acceleration. So this is just direct substitution. The mass is 4 kgs. The acceleration is 1.23. If you put that in your calculator, you will have 4.92 newtons. And just like that, we have the magnitude of the net force acting on the 4 kg block. The question we are really interested in, 3.4, calculate the coefficient of kinetic friction between the 4 kg block and the surface. Right, let's go ahead and take a look. So for the 4 kg block, we have F net being equals to ma. What is pulling the 4 kg block is the tension force. So we're going to have the tension force minus the frictional force minus weight parallel being equals to ma. We calculated the net force in 3.3. So this is 4.92. So the tension, we calculated it above also. That is 30.39, right? So we're going to have 30.39 minus the frictional force. We don't have the frictional force, so there's nothing we can substitute there. Let's find the frictional force first, and then after finding the frictional force, we're going to find the coefficient of kinetic friction. Minus weight parallel. Weight parallel is mg sine of theta. So that will be 4 multiplied by 9.8 multiplied by sine of 18 degrees. This is equals to 4.92. So 30.39 minus 4 multiplied by 9.8 multiplied by sine of 18. Let me put that in my calculator. 4 multiplied by 9.8 sine of 18 degrees. I have minus frictional force plus 18.2765 being equals to 4.92. So let's take these to the right hand side. So minus the frictional force being equals to 4.92 minus 18.2765. So minus the frictional force is equals to 4.92 minus 18.2765. This is minus 13.3565. And just like that, we have the frictional force. Now that we have the frictional force, we can go ahead and try calculating the coefficient. It should be an easy task when we have the frictional force. Okay, let's go ahead and take a look. Let me just drag these upwards. We know fully well that the frictional force is equal to the coefficient multiplied by the normal force. So the frictional force, that is 13.3565 being equals to the coefficient. The coefficient is what you're interested in. The normal force is mg cos of theta. So that will be 4 multiplied by 9.8 cos of 18 degrees. So we're going to divide both sides by the coefficient. Well, I almost said the coefficient of kinetic friction. Well, that's what it is, but let's just say we're going to divide by 4 multiplied by 9.8 multiplied by cos of 18 degrees. So we are dividing by 4 9.8 cos of 18 degrees. These are gonna cancel out. So 13.3565 divided by 4 multiplied by 9.8 multiplied by cos of 18. Let me just put that in my calculator, and I'm getting the coefficient being equals to 0.358. So that's 0.36. And there we go. We have our final answer. There's no SI unit for the coefficient of kinetic friction, so we leave it like that. What do you think will happen to the frictional force experienced by this object if we increase the angle? Will it also increase or will it decrease? Those are one of the questions you are most likely to come across in the exam. But before you see me answer that question, just leave a comment and let me know what you think. If we increase the angle, will the frictional force experienced by the object increase or decrease? And why are you saying so? Just leave a comment and let me know. Taking a look at the first question, 3.1, define the term static frictional force. Nothing hectic, we just reciting the definition as it is from the exam guidelines. So static frictional force is the force that opposes the tendency of motion of a stationary object relative to a surface. You state it like that. The static frictional force is the force that opposes the tendency of a motion of a stationary object relative to a surface. So that is 3.1. Let's go ahead and take a look at 3.2. Draw a labeled free body diagram of all the forces acting on the trolley at the top of the ramp, just as it starts to roll down the ramp. So let's go ahead and take a look. National building regulations for trolley and wheelchair ramps specify that the ramp must be 6 meters in length, while the angle of the ramp must be 4.76 degrees. The combined mass of the trolley and its contents is 80 kg. The coefficient of static friction between the wheels of the trolley and the ramp is 0.1. So there we go. That's the information we have. How do we then draw our free body diagram? Let's go ahead and take a look. So before we even start thinking about anything else, we know for sure that we have the weight, right? So let's go ahead and have that. The weight points straight downwards, regardless of the situation you have. So we have the weight. The object is resting on a surface, so we should have a normal force perpendicular to the surface. So there we go. It is the labeled free body diagram for all the forces just as it starts to roll down the ramp. When it rolls down, obviously we have the frictional force in the opposite direction, right? Maybe we can talk about why the frictional force will be pointing upwards. So let me just label these forces first and then we will address that. So we have the weight, the normal force, and we are saying that the frictional force is pointing up the incline. So why are we saying that the frictional force is pointing up the incline? Why is this the case? Let's talk about that. So the normal force is perpendicular to the surface, so it plays no role on the parallel motion of the object relative to the surface. What plays a role is the weight. And why am I saying so? We can resolve the weight into its parallel component and its perpendicular component. By looking at this, you can see clearly that the weight parallel is down the incline, and the object, or the trolley rather, will be moving down the incline because of that force. There is no other opposing force, so it will move down the incline, right? So that is why we are saying that frictional force is up the incline, because weight parallel is down the incline, and it's the only force that is doing work on our object down the incline or along the horizontal axis. That is 3.2. And 3.3, while the trolley is at the top of the ramp, calculate the magnitude of the maximum force of static friction. So if we want frictional force, we take the coefficient and multiply it by the normal force. The coefficient is 0.1. It is given to us in the equation statement. Here it is. So we just need to calculate the normal force. In an inclined surface, the normal force is mg cos of theta. So the frictional force will be the coefficient multiplied by mg cos of theta. Right. If you don't understand where this is coming from, go ahead and watch my video on how to calculate normal force on different cases. That's probably one of the most important videos I've ever made. But anyway, let's go ahead and substitute. The coefficient is 0.1 multiplied by the normal force. The mass is 80 kgs. Gravitational acceleration 9.8 multiplied by cos of, let me open brackets, cos of 4.76 degrees. Now it's just a matter of putting that in your calculator and you should get 78.13 newtons. Sometimes when you substitute, you can make a mistake. So if you can, well, you always can, substitute twice in the calculator. Put those things twice in the calculator and just see if you get the same answer. So 78.13 newtons. Right, I'm still getting the same answer. So now I'm confident that my substitution was correct. And now the interesting question. This is the question we are really interested in, right? If the ramp is longer than 6 meters, a less steep gradient is required. For a ramp of a less steep gradient, state whether the following would increase, decrease, or remain the same. If it is less steep, right, our angle, this 4.76, it decreases if our ramp should be less steep. So we are saying what will happen to the coefficient of static friction and the force of static friction if theta decreases, right? You need to understand what the consequence of a less steep gradient will imply. Theta decreases. So the coefficient of static friction, remains the same. And why do we say so? We're saying so because we know fully well that it is dependent on the material used. If you want to change the coefficient of static friction, you change the material, right? If the material is still the same, if it still have the same surface, then the coefficient of static friction remains the same. And then now let's talk about the force of static friction. Let's go ahead and take a look. We know that it is given by the coefficient multiplied by the normal force, of which we have the coefficient multiplied by the mass multiplied by gravity multiplied by cos of theta. So take a look at this. We know that the coefficient will stay the same. The mass stays the same. The gravitational acceleration stays the same. So it's up to cos of theta to be quite honest, right? Well, let me not say to be quite honest, like I would lie. Obviously, what I'm saying is true. It is scientific. You can see in front of you that what is affecting the frictional force is the angle. The coefficient, the mass, and the gravity will remain the same. So when the angle decreases, what will happen to cos of theta? Well, cos of 0 is 1 and cos of 90 is 0. So as the angle decreases, cos of theta increases, right? So we can say here that the force of static friction increases. And why do we say that it will increase? Because the normal force increases. Normal force increases, right? Because this is the normal force, and as the angle decreases, the normal force will increase as cos of theta increases with a decrease in theta. So there we go. We have answered the question. Did you get it right, or did you make a mistake somehow? If you got it wrong, I hope you see the mistake you made or the misconception you had, and now you have a bit of clarity. I think definitions like static friction is one of those things that people overlook, right? People usually concentrate on Newton's first law, second law, third law, so on and so on. But these kind of definitions are definitions that people oftenly overlook. They don't really give themselves some time to actually go through and memorize these kind of definitions. So I'm expecting that a lot of people actually got 2.1 wrong. But anyway, stories. Let's take a look at 2.2. Draw a labeled free body diagram showing all the horizontal forces acting on the crate just before it starts moving. Right. 2.2. Just like 2.1. People are not paying attention to the details. So I think that this is another question where people got it wrong. But most people think they got it right, but they actually got it wrong. Let me show you why. So 2.2, the key word here is horizontal, right? We want to draw a free body diagram showing all the horizontal forces. So if you include the vertical forces, I'm assuming you'll probably get it wrong, right? You'll probably lose 1 mark for every vertical force that you include. I think that's probably what's going to happen. So if you include the normal force and the weight, I think you're going to get nothing, or at most 1. But I'm quite sure there's no way you get all the marks if you include the vertical forces. So free body diagram for this object. Let's read through the question statement and see what is happening. In an experiment, a crate of mass 8.5 kg lying stationary on a rough horizontal table. So already we know that we are supposed to have friction, right? Because it acts horizontal. It is connected to a mass hanger by means of a light inextensible string passing over a frictionless pulley, as shown in the diagram below. Mass pieces are added to the mass hanger and the acceleration of the crate is measured. The experiment is repeated several times by adding different masses to increase the hanging mass each time. Ignore the effects of air friction. So right, that is the information we have. And then we're supposed to draw a label free body diagram acting on the crate just before it starts moving. Okay, so obviously we have the tension, right, as a consequence of the light inextensible string that connects the crate and the mass hanger. And then we also have frictional force, right, acting on the object. So there we go. These are the only 2 forces that we're supposed to have: frictional force and the tension force. Right, no normal force, no horizontal force. Not because they are not there, not because they do not exist. They still do exist, but the question is saying only the horizontal forces. So we have to respect that. And then 2.3.1. We're supposed to calculate the coefficient of static friction. So we are looking for this coefficient of static friction. So we already know fully well that the static frictional force is equals to the coefficient of the static friction multiplied by the normal force. The coefficient of static is usually greater than the coefficient of kinetic. Right. You will see why I'm mentioning that in this question as we do 2.3.2. So what information do we have? Do we have the frictional force? Maybe. Let's take a look and see what we have here. We are actually not given the frictional force, right? The static frictional force. So how the hell are we supposed to calculate it? But do we have the coefficient? The coefficient is what we're interested in. So obviously we don't have that. What about the normal force? Well, the normal force, we can calculate it, right? Because there's no Fy, the normal force is just going to be equals to the weight. So the normal force, 8.5 multiplied by 9.8. So let me just put this in my calculator and see what happens. My calculator is in scientific, so let me put it back to normal. So we have 83.3 Newton. This is the normal force. And then the coefficient is what we're interested in. So how can we calculate the static frictional force? How can we possibly calculate that? Okay, let's take a look at our scenario here. In 2.2, we have a free body diagram, right, of the crate just before it starts moving. Just before it starts moving, the frictional or the static frictional, it is supposed to be, because it's just before it starts moving, should be equals to the tension, right? But how can we calculate the tension? We are given this diagram here, right? You can see that when the hanging mass is 4.2, our crate starts moving, because that's where we start having a bit of acceleration, right? Right here at 4.2. So the static frictional force is equals to the tension, right? But the tension here on the mesh hanger with the mesh pieces is just equals to the weight, right, of that object. So that is, what is the mass of that thing? Let's take a look. Oh, the mass is 4.2 when we start having an acceleration, and acceleration due to gravity is 9.8. So we have 4.2 multiplied by 9.8, which is equals to 41.16. So we have the static frictional force. So now we can see 41.16 is equals to the coefficient multiplied by 83.3. So the coefficient is going to be equals to 41.16 divided by 83.3, which is equals to 0.49. So that is 2.3.1. Let's take a look at 2.3.2. We are looking for the magnitude of the acceleration represented by y on the graph if the coefficient of kinetic friction between the crate and the table is 0.4. So take a look at this. The coefficient of kinetic friction is 0.4, and we calculated the coefficient of static friction to be 0.49. So we are quite convinced that the answer we have in 2.3.1 is correct, because if the coefficient of kinetic friction was greater than this one for static friction, we should be worried, because we know fully well that that should not be the case. So there we go. We have the coefficient of kinetic friction, and then what else do we have? We are looking for the acceleration at y. So we do have the mass, we have the hanging mass, right? So the hanging mass is equals to 7.4. Let's concentrate on the crate. If we concentrate on the crate, F net is equals to ma. We know that fully well. And then the force that is pulling the crate is the tension minus the frictional force that opposes. And this is equals to ma, right? So what is the tension? We don't have the tension at this point. What about the frictional force? We have the coefficient, right? So this is 0.4 multiplied by the normal force, which is 8.5 multiplied by 9.4, 9.8, 83.3. So we have 83.3, and then this is equals to 8.5a. So tension minus, so 0.4 multiplied by 83.3, and this is equals to 33.32, and this is equals to 8.5a. Okay, so it seems like we are in a we are stuck here. We have the tension, we have the acceleration, and we have two variables, right? So we need another equation. So let's concentrate on the mass hanger. The mass hanger, the free body diagram, it should be the weight and the tension, right? So why is it going down? It is going down because of the weight. So weight minus tension is equals to 8.5, not 8.5a, but the mass of the hanger, which is 7.4a. So the weight 7.4 multiplied by 9.8 minus the tension is equals to 7.4a. Okay. Obviously, in place of tension, we can substitute, we can make the tension the subject of the formula in this equation. So it is going to give us 8.5 acceleration plus 33.32. So instead of having tension there, we can say 7.4 multiplied by 9.8, which is 72.52, minus 8.5a minus 33.32 is equals to 7.4a. So minus 8.5 minus 7.4, and that is minus 15.9a. This is equals to 72.52 minus 33.32. It is equals to 39.2. But when you take it to the other side, it is going to be minus 39.2. So the acceleration is equals to minus 39.2 divided by 15. Is this 15.9 or 15.19? I forgot what that it is, what I wrote there, because it's not clear. So minus 39.2 divided by minus 8.5 minus 7.4. I can just do that because I'm not sure what I wrote there anymore. So the acceleration that I'm getting is 2.47 meters per second squared. That is the answer to 2.3.2. And here's the question for you, 2.4. A 5 kg block is now placed inside the crate and the experiment is repeated. How will this affect the maximum static frictional force now experienced by the crate? Okay, choose from increases, decreases, or remain the same. Give a reason for your answer. So what is your answer to 2.4? And why are you saying so? Apart from that, let me know which question you want me to do next. Here we go. For past papers and study material, go to allpastpapers.com. I've already solved this entire question paper. If you want the memo, which I'm going to upload very soon on the website, go to allpastpapers.com. Here we go. So a block of mass 5 kg is at rest on a rough horizontal surface. When a constant force F of magnitude 18 Newton acts on the block at an angle theta to the horizontal, the block experiences maximum static friction. See the diagram below. 2.1 State Newton's second law of motion in words. 2.2 Draw a label free body diagram showing all the forces acting on the block. So 2.2, obviously we are going to start with the weight and we will figure out everything after that. Is the object resting on the surface? Yes, it is. So we are going to have the normal force. Obviously the applied force is right in front of us, so we have force applied. It is said that there is a maximum static friction, so we should have the frictional force that acts in the opposite direction of the applied force. That is 2.2. There should really be no questions when it comes to this. This is a very basic question. Grade 11 work, you have been drawing free body diagrams in grade 12 as well. 2.3, 2.3.1. The horizontal component of the force F is 50 newtons. Calculate theta. Right, so we need to know what the horizontal component gives us. That is Fx. So Fx is equals to 15 newtons. I kid you not, someone will say Fy is equals to 15 newtons and everything will just fall apart. But anyway, Fx is equals to 15. So that is F. This is a flat surface, not an incline. So the x component is actually cos of theta. Right, this is equals to 15. So the force applied is 18 newtons. Cos of theta is equals to 15. Right, so theta will be equals to cos inverse of 15 over 18. So theta is equals to, so 15 divided by 18 cos arc, that is 33.56 degrees. 2.3.1. Let's take a look at 2.3.2, the coefficient of static friction. Okay, we've solved one question, 2.3.1. We might have forgotten or lost some information as we were solving 2.3.1. So it's quite important for us to go through the question statement once more. A block of mass 5 kg is at rest on a rough horizontal surface. So the block is at rest. When a constant force F of magnitude 18 Newton acts on the block at an angle theta to the horizontal, the block experiences maximum static friction. See the diagram below. So the block still stationary. So F net is equals to MA. Which forces are acting on the block as far as the horizontal is concerned? That will be Fx minus F aesthetic, the maximum static friction, right? So Fs is equals to Ma. I don't think we are going to have issues with the subscript. Whether you write Fs, Fr, I think you're going to be fine, because that's not really the point. It's not like you're writing N, right? Or something which it's totally different and mean something completely different. Fs, Fr, you should be fine really. So Fx, that is 15 newtons, minus Fs, and then this is equals to Ma, stationary, so that is equals to 0. So Fs is equals to 15, but Fs, we know that this is the coefficient multiplied by the normal force, which is equals to 15. So the coefficient multiplied by the normal force. If you are a member of my Patreon, if you've been watching my course, you will know fully well that the normal in this instance is not just mass multiplied by gravity. It will actually be the mass multiplied by the gravity minus the y component of the force applied. because the force applied is above the x-axis. If it was below the x-axis, it will be the normal, it will be the weight plus the y component. But then in this instance, it is minus. So the y component is 18. And then because this is a flat surface, we have to use the sine. Sine of what? 33.56. And then this is equals to 15. So the coefficient is equals to, so 15 divided by 5 multiplied by 9.8 minus 18 sine of 33.56. This is 0.38. So there we go. That is the answer to 2.3.2. 2.4, angle theta is decreased while the magnitude of force F remains constant. How will the friction acting on the block be affected? Choose from increase, decreases, or remains the same. Explain your answer. So let me know in the comments, which option did you go with? Increases, decreases, or remain the same? Let me know in the comments. For past papers, go to allpastpapers.com. If you want to download the entire memo to this question paper, go to allpastpapers.com. Let me know which question you want me to do next in the comment section. Here we go. 999 out of 1,000 times, if you have a free body diagram, supposed to draw a labeled free body diagram, and it is out of 5 marks. On your free body diagram, you should be expecting 5 forces. 4 marks, 4 forces, 3 marks, 3 forces. That is the trend. Okay, so let's take a look at this one. 2.2, draw a labeled free body diagram showing all the forces acting on block A while it accelerates to the left. So we haven't even read the question statement, but let me show you something. I can start drawing my free body diagram. What do I mean by that? I know fully well that the weight is gonna be there, so I don't need to read the question in order for me to put the weight on my free body diagram. I can put the weight and think about everything else after, because I know that the weight is going to be there. It's not up for discussion. The earth is going to be pulling the object towards itself. So now let's go ahead and take a look at our question statement so that we can identify all the other forces. Block A of mass 4.1 kg is connected to block B of mass 2.3 kg by a light inextensible string passing over a frictionless pulley. Block A is at rest on a rough horizontal table. So hearing that at rest on a table, normal force, that is the first thing. And we already know from the question that it is accelerating to the left. So if it is accelerating to the left, the frictional force must be to the right. So there we go, we have the frictional force. A and B are connected by a light inextensible string. So we have the tension force. There we go. And then a force F of magnitude 49 newtons is applied on block A. So there we go. Our force F of magnitude 49 newtons. So this is force applied. Let's take a look. 1, 2, 3, 4, 5. 5 marks, 5 forces. I think we are good to go. Let's go ahead and do 2.3. So 2.3.1, we're supposed to calculate the magnitude of the kinetic frictional force acting on block A. So let's go ahead and do that. Quite an easy question. I would assume the frictional force is equals to, well, the kinetic frictional force is equals to the coefficient multiplied by the normal force. The coefficient between the surface of the table and block A is 0.35. So the coefficient is 0.35. All we need is the normal force, and we have answered our question. The normal force in this case is not going to be equals to mass multiplied by gravity because of this force applied. Okay, let me show you. The normal force plus the y component of the force applied. We can resolve the force applied into its components. They're going to be equals to the weight because the object is neither moving up or down. So by saying this, we're saying that the normal is the weight minus the y component of the force applied. So what is the weight? the weight is the mass, 4.1, multiplied by the gravity, which is 9.8, minus the y component of the force applied. The y component is going to be 49. So in a flat surface, cos is x and sine is y. So sine of 50 degrees. So let me get rid of this. I was just showing you how the normal force is coming about. So the frictional force is going to be equals to 0.35 multiplied by 4.1 multiplied by 9.8 minus 49 sine of 50. What do I get? 0.93. So 0.93 newtons. We're only interested in the magnitude, no need for direction. So there we go. That is 2.3.1. But what about 2.3.2? What does the question say? Acceleration of block A. We want to calculate the magnitude of the acceleration of block A by applying Newton's second law to each block separately. I guess people, they don't know that they're supposed to apply Newton's second law to each block separately. You know, the question even states apply Newton's second law to each block separately. I thought we all knew that, but it seems like we didn't. But anyway, stories. Block A, let's apply Newton's second law and see how it goes. So we're going to have F net being equals to MA. Well, the force that is pulling the object minus all the forces that are opposing. That is how I usually say it. So the force that is pulling the object here is the y, not the y, but the x component of the force applied, FAX. So we have FAX minus all the forces that are opposing the motion of the object. So which forces are opposing the motion of the object? The forces pointing in the opposite direction. So in this case is the tension and the frictional force, and this is equals to MA. So FAX, that is going to be 49. We said that x is cos, so cos of 50 minus the tension. I don't think we have the tension. Minus the frictional force. The frictional force is 0.93. This is equals to MA, so 4.1 the mass, and the acceleration is also unknown. Okay, I guess we can solve these and yeah, move to object B. So let's do that. 49 cos of 50 minus 0.93. Am I doing that in the correct order? I think I am. So we get 30.5666 if we round off to 4 decimal places, minus the tension being equals to 4.18. So this is our equation 1. Let's take a look at B. So B, what's happening at B? We have the weight, obviously, and we have the tension force. Am I missing something? Obviously, we don't have the normal, it is hanging. We don't have any frictional force, it's not in contact with F law. So I think there we are. So are we moving at a constant acceleration? No, we are not. But the blocks are moving to the left, so B should be moving up. So the tension, well, let's start by saying F net is equals to MA first. And then the force that is pulling the object is the tension, and the weight is opposing, and this is equals to MA. So what is their tension? The tension is unknown. The weight is 2.3 multiplied by 9.8. This is equals to 2.3A. So tension, what is 2.3 multiplied by 9.8? That is 22.54. So minus 22.54 is equals to 2.3A. So let me, okay, I can make, what do I want to calculate? I want to calculate the acceleration. So I can make the tension the subject of the formula in this equation and then substitute into the first equation. Or I can just add the two equations. But in this case, I think it is easier if I make tension the subject of the formula. So T is going to be equals to 2.3A plus 22.54. Even if you add the two equations, it would still be fine. I think this is the first time I'm actually doing this. Usually I just add the two equations, but it doesn't really matter, right? The math is correct, we know that for sure. So if we substitute this t in equation 1, we get 30.5666 minus the tension, which is 2.3a plus 22.54. This is equals to 1, not 1, but 4.1a. Right, so 30.5666 minus 22.54. This is 8.0266, and it is equals to 4.1 plus 3 point, not 3 point, but 2.3. This is 6.4a. So a is equals to 8.0266 divided by 6.4, and this is equals to 1.25 meters per second squared. There we go. Tell me, which video do you want me to do next? I'm waiting. A block of mass 2 kg is sliding down a plane inclined at an angle of 30 degrees to the horizontal, as shown in the diagram below. And then there's a coefficient of kinetic friction between the block and the plane, which is 0.2. Then the first question, 2.1.1, we're supposed to define the term kinetic frictional force. So kinetic frictional force is the force that opposes the motion of a moving object relative to a surface. Let's go ahead and look at 2.1.2. Draw a labeled free body diagram for the block while it is in motion. So the marker location is 3. And like I've said previously, if the marker location for a free body diagram is 3, then you should know that your free body diagram will have 3 forces. If the marker location is 3 and you have 2 forces on your free body diagram, you're doing something wrong. And another point I always make is that when you're drawing the free body diagram, before you start thinking about a lot of things, put weight first. Everything is going to come after you put weight. Right, and then now we can go ahead and look at our object. Is our object resting on a surface? Yes, it is. So we have normal force right here. What else do we have? We have the coefficient of kinetic friction, so we have friction. The object is going down the incline, so our friction must be up the incline. So we have frictional force up the incline. Obviously, with our weight, we know that we have the perpendicular component, FG perpendicular, and the parallel component, FG parallel. You don't have to include FG parallel and FG perpendicular, but most likely you will have to use it when you calculate. Let's do 2.1.3. Calculate the acceleration of the block. Right, before we start analyzing our problem, F net is equals to MA. These are just standard things. Now we can go ahead and analyze our problem. We have FG parallel and we have the frictional force. Those are the two forces we are interested in. Why am I saying so? Our object is moving parallel the incline. So we are only interested in the forces that are moving parallel the incline. Right, so how do we then set up our equation? So what you want to say here is that the force pulling the object minus all the forces that are opposing. As you can see, the object is going down the incline. This is because of FG parallel. And then the force that is opposing is the frictional force. So we're going to say FG parallel minus frictional force is equals to MA. Now we just need to find FG parallel. Let's do that separately. So FG parallel is equals to mg sine of theta, where m is the mass, 2 kgs, multiplied by 9.8 sine of 30 degrees. So what is FG equals to? This is 2 multiplied by 4.9. And then now we can calculate frictional force. Frictional force is equal to the coefficient multiplied by the normal force. The coefficient is 0.2. And then our normal force, if you look at our free body diagram, the normal force is being balanced out by Fg perpendicular. So the normal force is equal to Fg perpendicular in this instance, where Fg perpendicular is mg cos of theta. So we have 2 multiplied by 9,8 multiplied by cos of 30 degrees. So our frictional force is equal to 2 multiplied by 1.6974. So now we can substitute back into our equation. Fg parallel, that is 2 multiplied by 4.9 minus the frictional force, that is 2 multiplied by 1.6974. This is equals to ma. The mass of our object is 2 kgs. The acceleration is what we are interested in. It will be easy to see what we need to do here. We are dividing by 2 on both sides. So let's just go ahead and do that. And we get in an acceleration that is equals to 3.2 meters per second squared down the incline. This right here is 4.9 and not 14.9. But anyway, stories, that is 2.1.3. Let's do 2.2. In two adjacent buildings of the same size, the two walls nearest one another are 7 meters apart, and the walls furthest from one another are 35 meters apart, as the diagram below illustrates. Right, we can see them. And then the question is saying, use an appropriate calculation to show that the gravitational force that the two inner walls exert on each other is 25 times bigger than that of the two outer walls on each other. And then they're saying we need to show that Fg of the inner walls is equal to 25 times of the outer walls. What is Fg? Let's start there. Fg is equal to G m1 m2 divided by r squared. So everything else is constant except from the distance between the two walls. So that is the only variable we are changing. Let's start with the inner walls. So for the inner walls, we're going to have Fg of the inner walls being, let's just say Fg inner, being equals to G m1 m2 divided by r squared. The inner walls are 7 meters apart. So we're going to have 7 squared. We know what 7 squared is equals to. So we're going to have G m1 m2 divided by 49. These are the inner walls. Now we can go ahead and set up the same equation, but now for the outer walls. The outer walls are 35 meters apart from each other. So we're going to have Fg of the outer walls being equals to G m1 m2 divided by 35 squared. So G m1 m2 divided by, what is 35 squared? That is 1225. So here we have Fg for the inner walls, and here we have Fg for the outer walls. Now we need to show that Fg for the inner walls is equals to 25 multiplied by 25 multiplied by Fg of the outer walls. Let's go ahead and see if this is true. So Fg of the inner walls, we have G m1 m2 divided by 49. This is apparently supposed to be equals to 25 multiplied by G m1 m2 divided by 125. G m1 m2 divided by 49 is indeed equals to G m1 m2 divided by 49. I think I've defined Newton's second law of motion more than 100 times. So for this video, let me just skip it. Only these ones. Let's start with 2.2.1. The coefficient of kinetic friction between the slope BC and the block M2 is 0.2. Draw a labeled free body diagram for block M2. Let's go ahead and take a look at block M2 and see what we can do. So before we start thinking of anything else, we need to indicate the weight first. After indicating the weight, we can then look at the other forces. Our object is resting on a surface, so we expect a normal force. M1 and M2 are connected by a light inextensible string, so we are going to have our tension force. The mass of M2 is 70 kgs. The mass of M1 is 12 kgs. So it would make sense to assume that M2 is moving down the slope. If that is the case, then the frictional force will be up the slope. 2.2.1, it is for 4 marks, and we have 4 forces on our free body diagram. So we are quite confident that we have not missed anything. Let's go ahead and do 2.2.2. Calculate the magnitude of the acceleration of the system. Show all steps in your calculation. Well, let's start with M2 because we already have a free body diagram. So this is for M2. Why am I writing M2? I want to show the person that is marking my script exactly what I'm talking about. Yeah, I don't want any confusion whatsoever. So F net is equals to MA. This is how we always start. What do we say now? We say the force pulling the object minus all the forces that are opposing. M2 is sliding down the slope. That is due to the parallel component of the weight. So we have FG parallel minus the frictional force minus the tension force being equals to MA. So how do we calculate FG parallel? That is mg sine of theta. So we're going to have 70 multiplied by 9.8 multiplied by sine of 30 degrees minus the frictional force. The frictional force, that is the coefficient multiplied by the normal force. Our coefficient is 0.2. The normal force is mg cos of theta. So that will be 70 multiplied by 9.8 multiplied by cos of 30 minus the tension being equals to 70 multiplied by a. We're going to have 224.1813 minus the tension force being equals to 70A. As you can see, we have 2 variables but 1 equation. We need 2 equations. Let's name this equation 1 and set up our equation 2. We're going to find equation 2 using M1. Let's draw a free body diagram for M1. We have the weight, obviously. We have the tension, which is pulling it up the incline. We have the normal force. M1 is experiencing no frictional force, so we can leave it like that. When we set up our equation, the force that is pulling M1 is the tension minus the force that is opposing, the parallel component of the weight. So we have FG parallel being equals to MA. We're going to have the tension minus FG parallel. The mass is 12 multiplied by 9.8 multiplied by sine of theta. The angle of inclination is 50 degrees. So we're going to have sine of 50 being equals to 12A. So we're going to have the tension minus 90.0868 being equals to 12A. This is our equation 2. Let's add the 2 equations. We're going to add the left hand sides together and the right hand sides together. Minus tension and plus tension will cancel out. We're going to be left with 224.1813 minus 90.0868 being equals to 82A. This is just 134.0945 being equals to 82A. We need to divide both sides by 82, obviously. And if we do that, we're going to get an acceleration that is equals to 1.64 meters per second squared. We are only interested on the magnitude. We don't need to indicate the direction. 2.2.2, let's do 2.3. So 2.3 is saying that if the angle of slope BC is decreased to 20 degrees, initially it is 30 degrees and now it is being decreased to 20 degrees. Will the frictional force between the block and the slope increase, decrease, or remain the same? Explain your answer. So the frictional force is going to increase. Let me show you why. The frictional force is equals to the coefficient multiplied by the normal force. The coefficient, it depends on the material. So whether we increase or decrease the angle, the coefficient is not affected. So now we are only looking at the normal force. Well, the normal force is equals to mass, gravity, and cos of theta. Well, the mass is constant and the acceleration is also constant. So we are just looking at cos of theta. If the angle decreases, does the normal force increase or decrease? We know that cos of 0 is 1 and cos of 90 is 0. If you decrease the angle, the normal force increases. If you increase the normal force, the frictional force is going to increase.